All right, so we're going to quickly review this transformation of the metric. I kind of noticed something in the last lecture that I probably should have highlighted a little bit, but I promised you we would go through this again a few times because it's such an important point. So I'm going to start with just the, I'll just write down the basic proof that we did last time, and we'll pick it up from there. So we will start with a vector space with a given basis E mu over a certain field, with the usual caveat that we're going to always be considering quaternions as a possible member of this definition of fields. If this vector space will have an inner product, which is well defined. It'll be in n dimensions, and of course it has its own vector space scalar multiplication and a vector addition. All right, so what do we start with? We start with a vector space, n dimensions, with a basis E sub mu, with the vector addition and vector scalar multiplication, with a inner product, and it's over a field with the caveat that we'll always consider quaternions as a possible scalar for the vector field, or for the vector space. I almost said vector field, but I meant vector space. The metric is defined as the inner product's value over the basis vectors, and it's given with two lowercase indices, Gij, which reflects the fact that this can be understood as a rank 0-2 tensor. Then we start asking the question we ask all the time, which is, if I have a member of the general linear group in n dimensions over F, a single member of that represents a transformation under the vector space. It's a basis transformation. That's the definition of what these things are. So A is a mapping that takes two vectors and returns another vector. So I want to ask the age-old question, what happens to these values when I transform the basis from the unprimed basis to the prime basis? And what we come up with is this. We write the hat. I said prime, but I prefer hat for the purposes of this whiteboard. The hat value of Gij is defined by definition, the new basis, the hat basis. But the hat basis is clearly defined in terms of the unhat basis via this matrix. And we write it now in full matrix notation, right? So AJK is how we write a matrix in the work we do. Lowercase j, uppercase k. That is what a basis transformation looks like using all the notation consistent with everything we've done in the past. It's got a lower index and an upper index, and those guys can fully be interpreted as a regular linear algebra matrix, right? When you have two lower indices, you can't do that. You can't interpret this as a regular linear algebra matrix. I'm really tempted to go into detail on that in a few minutes. But this is what we have. Now we assume that this metric, whatever it is sesquilinear. Therefore, the sesquilinear means this guy comes out on the right with the involution, or the complex conjugation. And this guy comes out on the left without the complex conjugation. And you get this thing, right? You get this thing. Definition, we're assuming now that we've added a sesquilinear metric. So this is another assumption. So why don't I write that in here? This is sesquilinear, right? Sesquilinear. So now that we know that, I just replace this with its definition, which is GKL, right? GKL in the original basis. So I already know those numbers, presumably. And I end up with this. So I have the transformed metric components in terms of the untransformed metric components. Now, the part I didn't mention last time is, I kind of actually went a little bit too quick, right? What I said was, okay, now let's assume this really is a field in the sense that these guys commute. This is a member of the field, this is a member of the field, this is a member of the field. If the field's commuting, I can write this as such. And then I said, and that's the standard thing we remember from tensor analysis. This is how a tensor transforms under a change of basis. But that's not true, right? Because the tensor analysis we've done never involved a complex conjugation, right? What we did would look like this. I hope my eraser can squeeze in there. It would just be that, without the complex conjugation. But of course, the work we've done all was involving real bilinear metrics. And for a real bilinear metric, this the conjugate equals itself, right? The AJK bar equals AJK. There is no complex conjugate for a real or for a bilinear metric at all. Actually, I shouldn't even say it was necessarily real, but it was bilinear. All the metrics we considered in the past were bilinear metrics. This guy is a sesquilinear metric, and as such, you end up with the bar there. But this is all consistent. So I wanted to point out that I kind of glossed over that fact in our last lecture. But anyway, so this is that standard transformation. So then we ask the question about the constancy of the components. By constancy of the components, what I'm trying to emphasize is that Gij hat equals Gij without the hat, right? I want to show that this is the case, right? And so this basically means that G hat 1, 1 equals G11, right? G13 equals G hat 13, all right? It's as simple as that. I'm trying to show that you change the basis under A, these things don't change. What are the conditions that are required for that? So the first thing I'm going to do is I'm going to return this to its pure sesquilinear form to maintain full generality, right? Right now, this is no longer fully general. This would not work for the quaternions, right? It works for the real numbers because that bar is essentially meaningless. Works for the complex numbers because they commute. Does not work for the quaternions. And that's not how Gilmore writes it in his book. So let's return to the Gilmore form. So Gilmore form would be, let's see, let's do this unambiguously so everybody can see. Oops. So there's no mystery about what's going on here. I take this A, move it there. Take the G, move it there. Take the A, move it there. Oh, I left a little bit behind. All right. So that is what we're working with. Okay. So so the next step is to do another transformation. What I'm trying to show is that if A, the linear transformation A, which is an element of the general linear group in n dimensions over the field, if this is true, then all of the matrices, remember this is a set of matrices, all the matrices A, right, form their own group, right? And then last lesson I explained that it was, I proved it was closed, right, which is a critical element of a group, meaning it's A is a matrix group's group operation is matrix multiplication, and under matrix multiplication, all the matrices that have this property form a group that's closed. So the next thing I do, obviously, is I find another matrix that is also a member of this group, G, L, N, F, and I do this again. I look for G hat I, J, which is going to be equal to G, I, J hat, which is going to equal G, I, J. And what is the expression for G hat I, J? Well, the expression for hat is exactly analogous to this, but with G hat in the middle. Let's see if I've got the analogy right. J. Ooh, I have two J's here. The first one here should be an I, right? Should be an I. Did I do that earlier? Where did this come from? Oh, up here. Yeah, this should have been an I, like that. And this is a J. Okay. So let's see. So you have the IJ, right? IJ matches with IJ. You're summing over this. You're summing over this second index. You're summing over this first index, and that's correct. Okay. So now I substitute for this. I have substitute this expression, and let's see if I got this substitution correctly. I had to change I and J from this one to NM. So I becomes let's see. Yeah, I becomes, so the L will be replaced with M, the K will be replaced with N. So KL has to be NM. So KL, I, J, M, N. Okay, and then B, J, N here, and then those cancel and those cancel, or sum out, sum out. Okay, so this is the thing. I think. So now with that, I just lose the brackets, right? I lose the brackets. And we now have that in order for this to be true, well, in order for, let's see, how does this work? In order for this to be true, I look at these two guys. And these are matrices, right? And I know how matrices work because I've studied my linear algebra. And I know that this is matrix multiplication. And so I can write this as a matrix B, the matrix B times the matrix A, and the remaining index is IL, and then this is GKL. And these guys are these guys here are the conjugations, right? This is the conjugation. So what I know about two numbers is the conjugation of the product is the product of the conjugations in the reverse order, right? So I have to reverse the order to get B, J, N, A, N, K, and then I do the conjugation of the whole thing, right? That is what this is. So then I can write that now as B, A, conjugate, and then the leftover elements are J, K, like that. Phew. Okay, and so what is the final result? Well, the final result looks exactly like this result. I mean, this is just another matrix, and this is another. We know that matrix multiplication produces another matrix, and this structure is the same as the other structure. So in other words, the product BA also preserves, right? If this preserves the metric, if A preserves the metric components and B preserves the metric components, then BA must conserve the metrics components. We've just shown it, right? We demonstrate this is BA and that is BA. And we got to this line by assuming this, right? So we know it's closed. And we have the same caveat that if we're dealing with a real vector space, this complex conjugation goes away. You can commute. These all becomes numbers at this point because they're matrix elements, so you can commute them all you want. The summation structure is what enforces the matrix multiplication that's going on. And then you have the regular basis change from the unprimed or from the unhatted basis to the double-hatted basis through these two matrices. Now we know matrix multiplication, since we know it's closed, we know matrix multiplication is associative, so it's closed and it's associative. We know that it has an identity because the identity matrix, this all works for the identity matrix just fine. So we have the identity. Now the question is there a unique inverse? That means if I have a matrix A that preserves the metric, is there a matrix A inverse that also preserves the metric that is inside that is inside the set of all matrices that preserve the metric? I guess we're looking for the set of all matrix A, right, that preserve the metric Gij, right? All the matrices that do that. So the question is in this set, is there an A inverse? We know that if there's an A and there's a B, there's going to be an AB. We know it's closed. We know the identity is in there, right? The question now is, are the inverses in there? So what we do is we say, well, A is a matrix, and it's a member of the general linear group n, with n dimensions over the field. Well, this is a group. We know that this is a group. So we know that A inverse, well, we know that A is invertible because it's a member of this group, which is by definition a set of invertible matrices. So we know an inverse exists. So let's call that inverse B, right? So I know a matrix B does exist. The question is whether or not B is in this set. In other words, does B have this property here? In fact, I used B in the previous proof and I assumed it did have the property, but now I'm calling B A inverse, right? And now I'm asking if this B, which also happens to be A inverse, does it share the property of A, which leaves these metric coefficients invariant. I forgot my my little g hat. Okay, so I forgot it here too. There it is. So the point is I can take that inverse matrix and I can multiply it on both sides of GKL. Damn, I'm forgetting a lot of little things. GKL. And so I start with the expression here where I transform the metric from the unhatted basis to the hatted basis. So I use A to do that. And then I take the hatted basis and I transform it using A inverse, right? And it shouldn't, I'm hoping that it doesn't change anything. So I take this expression and I jam it right in here. And then I take BSL and BKR, conjugate, and I multiply that. And then I kind of do the same thing I did up here, right? I end up with BA and BA, and I realize, this step is exactly this step right here, and I can now do this. But I know that BA and BA is the identity, right? I know it's the identity. So I know I'm going to end up with delta Sj Gij times delta R, undo, delta Ri, like that, which is going to be G, wait a minute. GSR, right? SR, right? GSR. Now notice, so this side ends up becoming G hat SR, right? G double hat SR. So meaning the transformation of the KL basis into the double hatted basis, which now gives me GSR, well, that equals the original GSR, which proves the whole point of this thing. So the inverse matrix is indeed, so the inverse matrix takes this and doesn't change anything. So it's obviously an element of this set of all matrices that don't change the basis. So if A is an element of the set of all linear transformations that don't change the, it changes the basis, but doesn't change the metric, then its inverse is also in that set. So now we've shown that it's closed, it's associative, the identity is obviously there, and it has unique inverse. Therefore, we know that this is a group, and that's the whole point. So the whole point is to understand that if you can find an element of the general linear group that leaves the metric unchanged, right? The set of all elements that leaves the metric coefficients unchanged, that set of all elements under the same is a subgroup of the general linear group, right? And that's going to be, I'll say, the set of these matrices is, let's see, I guess it goes the other way. It's a subset of the general linear group. And now this is important. Now the magic all happens right, let me see, where does the magic happen? The magic happens right here, obviously, in this statement, right? This is the defining property of a matrix that doesn't change the components of this metric. And obviously, this is extremely sensitive to a couple things. It's extremely sensitive to these values. You're summing over these values, and it's extremely, and once you know what these values are, you have to sort of find the matrices that make this true. But it all depends on these values. If I got to give you these guys first, I have to tell you the values of these matrix elements, or I shouldn't say call them matrix elements, a big mistake. These components, these inner product components, these metric tensor components is what they really are. I need to tell you what those values are, and then you can go out and look for matrices that leave those things invariant. And once you find one that does, its inverse is also going to leave that matrix invariant. And if you find two, you know that the product of those two is going to leave that matrix invariant. And in fact, when you find them all, you're going to realize that the collection of all of them form a subgroup of the general linear group. And so all of those groups we talked about, the special orthogonal group, let's see, I wrote them all down before, right? You know, SO, SU, UO, SL, the symplectic group, the the general linear group itself, obviously. All of these guys are subsets of the general linear group, but each one of them is created in order to leave a different kind of metric invariant. So there's really as many of these guys as we can kind of identify canonical versions of the metric. And that's sort of the next topic right now. The next topic is taking all the different possible metrics that we can think of that are reasonable to deal with, and then finding the various groups that leave all those different metrics invariant. And those groups are called the classical groups. So we have to. So our mission is really two parts. The first part is to classify all the different metrics. Right? We've got this idea of, oh, I've got a sesquilinear metric in this particular case. Well, I want to classify all of the different possible sesquilinear metrics if I can. I want to do my hardest work and best job of classifying all the metrics, the bilinear ones, the sesquilinear ones, the symmetric ones, the antisymmetric ones, and do the hardest work I can to classify the metrics. And then I'll be able to distinguish between vector spaces, because two different vector spaces, if I have two different vector spaces, V and W, if they're both the same dimension, they both have a basis, they both have the same field, these are really isomorphic, right? I'm really talking about the same mathematical structure under two different names. So, but once I give vector space V one inner product, say the V inner product, and W a different inner product, the W inner product, now these things are distinguished. So I have as many different vector spaces of n dimensions as I have really different kinds of metrics that I can impose on them. So I want to classify these metrics and then look for matrices, look for elements of the general linear group in n dimensions over the field that leave those matrices invariant under basis transformations. Because remember, I should be able to change the basis of a vector space pretty arbitrarily. But if the metric starts to change, that's a little different than I'm actually kind of changing the metric with the basis change. And I don't want to do that. I want to keep the metric components the same. So that's the name of the game. And we'll begin that next time. So, but before we get there, metric preservation is a critical property of identifying all of these classical groups. But there really are two critical properties. One we've already discussed, and that was called volume preservation, right? Where we're keeping the volume form unchanged. You may remember from a slightly earlier lecture here that if I make a change of basis and I look at the volume form, the exterior product of all n basis vectors, that when I use a matrix A to transform these guys, this volume form transforms as the determinant of A times the original volume form, the unhatted volume form. The only difference between the unhatted volume form and the hatted volume form is simply a factor of the determinant of A. So this is volume preservation. Gilmore calls this volume preserving group. So A is a volume preserving group, and that's all. Basically, that's all. If the determinant of A equals 1, you're volume preserving. If the determinant of A does not equal 1, you're not volume preserving. Meaning, if the determinant of A is -1, for example, not volume determining. If it's 10, not volume determining. If it's 1, volume preserving. So we have two ways of classifying our classical groups. One is those that are volume preserving, where this rule applies, and those that are metric preserving, where all of these various rules apply. And wherever you see these S's, right, these little S's, those are volume preserving groups. So you know, except maybe the last one, maybe this SP stands for the symplectic group. I'm not going to commit to the fact that the symplectic group always has a determinant of 1. I don't think it does. So all the ones that have an S are volume preserving. So they have a determinant. Those matrices have a determinant of 1, And we already know that matrices with a determinant 1 will form a group pretty quickly, meaning the product of two matrices with determinant 1 is a matrix with determinant 1. The inverse of a matrix with determinant 1 also has a determinant of 1, and all of those things. But it's these other letters, those are the parts that are where we talk about metric preservation. And this, as far as symplectic goes, it preserves a particular type of metric. Hold on. Yeah, the symplectic, because symplectic, we'll see later what this means exactly, but the symplectic group, it also has usually 2 n dimensions in some field, right? The symplectic group, because it has an S there, that doesn't mean it's volume preserving. That is the volume preserving version of the symplectic group. I'm just checking Gilmore. I hadn't thought about that notation before. Okay, so our next lecture, we actually are going to start burrowing down a little bit into the nature of these various groups, the orthogonal group, the unitary group, and the symplectic group.